In this video, I'm going to take a look at what happens if we multiply a 2D Cartesian vector by a scalar value. So if we had a 2D Cartesian vector, which I could call v, and we know, of course, this has an x component and a y component, being a 2D Cartesian vector. And if I had a scalar value, which I'm going to call s, this is just a single number stored in a variable called s. What I'm interested in is what happens if we multiply our vector by this scalar. Now, as we know, we could multiply this in two ways. We could take s and multiply it by v, or we could take v and multiply it by s. In both cases, by definition, they're going to result in a vector, and that vector is going to have the same number of components as the vector in our multiplication. So in our case, that vector result is going to have two components, and as we're actually going to see, by definition, they are commutative. That is to say, it doesn't matter which order we multiply these in, they are equal. But I am going to show why they're equal in a second. So let's pick on our first example here, s times v. So if we had s times v, we know that's going to give us s times our vector x, y, and we know that's equal to some result vector. So we have a vector as a result, and we know that the result has the same number of components as the vector in the multiplication. So in this case, our result has two components. But what are those components? Well, again, this is by the definition of how we multiply a scalar by a vector, and it's actually very simple. What we're going to do is we're going to, in this case, take our scalar value because it's first, and we're going to multiply it by each of the components of a vector in turn. In this case, we have two components, so we'll multiply it by the first component, and then we'll multiply it by the second component. So we're multiplying our scalar value by each component in turn, and that's going to give us the corresponding component of our result. So for the first component of our result, we're interested in the first component of our vector. We take our scalar value and we multiply it by the first component of our vector, and that gives us the first component of our result. So that is s times x. For the second component of the result, we're interested in the second component of our vector. So we take our scalar, we multiply it by the second component of our vector, and that gives us the second component of our result, which is s times y. So it's really very simple. What we're doing is we're taking our scalar, we're multiplying it by each component in our vector to generate the corresponding component in our result. What about the other way we could have multiplied this? V times s. So we'd have had xy multiplied by our scalar. This is going to work in exactly the same way, but in this case we're going to take each component of our vector, and because that comes first, we're going to multiply that by our scalar. So we're going to take x and multiply it by s, and each component in turn is going to be giving us the corresponding component in the result. So x times s, because x is our first component, that's going to give us the result of our first component as x times s. Then we're going to take y times s, because y is the second component. It's going to give us the result of our second component as y times s. Now what you'll notice is that here in our result vector, the first component of one of them is s times x, two scalar values. And you'll notice in the second, it's x times s. As I get rid of our circles, there we go. So we had s times x. In the second, we had x times s, the opposite order. But you'll notice, because these are just scalar values, and we know that scalar multiplication is commutative, we saw that in the first volume of this series, well, therefore, we know that s times x is the same as x times s. That is to say, the first component of this result is identical to the first component of the second result. But we can see the exact same thing here with the second component. We have s times y, which we know is equal to y times s. Scalar multiplication is commutative. That means we can switch the order of our operands and still get the same result. So not only is our first component of our equations equal, or rather of our result vectors equal, but the second component of our result vectors are equal. So that means that s times v is the same as v times s. They're both giving us the same vector, because we looked at vector equality right back in our introduction to 2D vectors, our 2D vector overview video, because we said for a vector to be equal, the first component must equal the first component of the other vector, and the second component must equal the second component of the other vector, and so on for each of the components. So here we're seeing that our first components are equal and our second components are equal. Therefore, these two result vectors are equal, and therefore s times v is equal to v times s, which all comes back round to saying that vector scalar multiplication is commutative. So once again, just to recap before I move on any further, if we have a vector and we multiply it by a scalar, it doesn't matter which order we multiply it in because it is commutative. It's going to give us a result. That result is going to be a vector. That vector is going to have the same number of components as the vector we're multiplying. In this case, that's 2 components. And we work out those components by taking each component in the vector and multiplying that by that scalar value and using that for the corresponding component in our result. So that's a simple look at vector scalar multiplication. But let's take another more in-depth look now at a couple of things. The first thing I want to look at is how does this relate to the graphical representation of a vector, because actually that's really quite interesting. The second thing I then want to take a look at is what happens if this scalar is a negative value. But before we do that, let's take a look at what happens to our graphical representation of these vectors when we're multiplying them. Now to do that, the easiest thing to do is going to be to actually use some real numerical examples. So I'm going to create a vector, and that vector is going to be 2 units in x and 1 unit in y. I'm going to create a scalar, and I'm going to say that this scalar is, I don't know, let's pick a scalar value of 2, for example. So if I was to draw a 2D Cartesian coordinate system, we know that we can represent our vector A as a directed line segment in this coordinate system. Now I'm going to need some units of measure in this system, so this should be plenty, but 1, 2, 3, 4, 5, and 6, and again in y, so again that should be plenty. Fantastic. So if I've got my coordinate system here, I can graphically represent this vector. Now, again, vectors are free to float around our Cartesian coordinate system, our 2D space. I'm going to be repeating that fact time and time and time again because it really is incredibly important to realize that these vectors are free to float around. But, of course, to draw them, I need to pick on some point in space to draw it from. So in this case, I guess we could start at 1, 1 in x, and if I draw our vector starting from there, we're going to be moving 2 units in x, 1 unit in y, and my vector is going to look something like this. So this is my vector A. Now what we're interested in is what happens to this graphical representation of the vector when I multiply it by a scalar. So we're looking at s times A. In that case, we know this is 2 times our vector 2, 1. So to calculate that, we know we take our scalar value and multiply it by the first component of the vector to give the first component of the result. So 2 times 2 is 4. We then take our scalar and we multiply it by the second component of our vector to get the second component of the result. 2 times 1 is 2. So this is the vector s times A, which is the vector 2 times A. And we can draw this vector in our Cartesian space as well. Now in this case, I'm going to start this at 2 in x and 1 in y. And we see we travel 4 units in x and then 2 units in y. So we travel 4 in x, 1, 2, 3, 4 onto here, and 2 units in y, 1, 2, like so. That's going to give us a vector like this. Now we know this vector is equal to 2 times a. This can actually be written simply as 2a. So this is 2a. Now what you'll notice about these vectors, and you might not notice it straight away, but there's actually some very interesting properties about these vectors. The first is that they're parallel to each other. They are traveling in the same direction. We can see that both a and 2a are travelling in that same direction. The second is that the length of 2a is different to the length of a, and it's actually very specifically different to the length of a. I'm going to need to erase this to demonstrate it, and I can write this above our vector. There we go. If we look at a, we know a moves 2 units in x and 1 unit in y. Let's count that out from the start of 2a. 2 units in x and 1 unit in y takes us right to here. So this would be a. If we then count another 2 units in x and 1 unit in y, it takes us to the end. So this is a. So you notice that 2a is equal to taking our vector a and then adding another vector a to it. So we start here, we travel one vector a, and then we travel another vector a afterwards. That's not by coincidence. If we think about this, the two properties we've just seen, the first is the direction doesn't change, the second is the length of the line changes. In actual fact, it changes directly based on the number we're multiplying by. If we multiply by 2, it's going to be twice as long. So we can see if we have 2a, we're actually getting twice the length of a. We're getting 2 of them. That's not by coincidence. It's actually by the fact of how we're multiplying these values. So let's think about it. When we're multiplying a vector by a scalar, we're multiplying each component of that vector by the same value. So that means we're not going to be changing the direction of the line, because the relationship between how far we travel in x and how far we travel in y maintains its proportionability. It will still travel the same distance in y for a single unit in x. That defines the gradient of a line. We saw that way back in volume 1. And because of that, it means the direction of our vector does not change. However, because we're multiplying each of the components by a value, we are changing the overall distance that we travel in x and we travel in y. And because of that, if we're changing the overall distance of our vector but not the direction of our vector, we can think of it as scaling the length of our vector. So that is really important. If we're multiplying a vector by a scalar, what we're doing is we're scaling the length of the vector. Now I am going to write this in mathematical notation, but really the important bit is the concept behind it, not the mathematical notation or the equation. The mathematical notation is just a way of summing up everything I've just said in English in terms of a few symbols. So the mathematical notation is if we have a scalar value multiplied by a vector, the length of the resultant vector is equal to our scalar multiplied by the length of the original vector. Now there's actually one extra addition I need to put in here. I'll come back and add that in a second. But for what we're dealing with here, we can see that if we have a vector and we multiply it by a scalar, the length of that vector times the scalar, the length of the result, is going to be equal to the length of the original vector multiplied by that scalar. So for example, here where we multiplied a by 2, the length of 2a is 2 times the length of a. Now why did I say I need to come back to this mathematical notation and add something in? Well, it's actually because when we're dealing here with finding the length of a scalar times a vector, we actually need to make sure we take the absolute value of that scalar, and that's denoted in a similar way to the length of a vector, a magnitude. It's denoted with a single vertical line. Now for those of you who haven't encountered the absolute value, I'm not going to go into detail on it, but needless to say, an absolute value is basically if we have a negative value, it's equal to the same as the positive value. It's just the value. So if we had the absolute value of -2, it's the same as the absolute value of 2. It's just 2. So what we're doing with an absolute value is we're ignoring whether it's positive or negative. We're just taking the size of that number and we're using that as a positive number. So if we have -2, the absolute value of -2 becomes +2. If we have -5, it would become +5. If we have a positive number, it just stays as a positive number. So we're basically ignoring any negativity on our value. But why is this important? Well, it all comes around to what happens if we have a negative scale factor. And to see that, we really need to look at some more examples. So I'm going to bring up a new whiteboard, I think, rather than try and squeeze that in. And let's take a look at what happens when we have a negative scale factor. So if I have some other vector, I'm going to pick b in this case, and let's make b 3 units in x and 2 units in y, for example. And I have a scale factor, a new scale factor, and in this case, I'm going to go with -2. So before, our scale factor was +2. This time, my scale factor is -2. So what I want to do is I want to draw some Cartesian axes and graphically represent b. I'm then going to work out what -2 times b is in terms of components, graphically represent that, and then we can look at the comparison between those two vectors and see why I made that distinction that we're using the absolute value. Hopefully everything will become very, very clear in a second. So I'm going to draw a set of Cartesian axes. So this is our x-axis, this is our y-axis, and here is our origin. So I also need some measurements on these axes, so this should be hopefully enough. And also on our y-axis. Let's actually label these. So 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7. Fantastic. So let's start out by drawing b. Again, it's free to float around in Cartesian space, but I need to pick a place for it so that I can draw it. In this case, I guess let's start with a value of 0 in x, 2 in y, and we know it travels 3 units in x, 2 units in y. I'm going to get a vector that looks like this. So this is our vector b. Now I'm interested in finding what s times b is, which we know is equal to -2 times 3, 2, which we know is equal to, that scalar value -2 times 3 is -6 for our first component, and that scalar value -2 times 2 is -4 for our second component. So now we can draw this vector. Now I'm going to pick the point 64 to start at, and we know that we travel -6 units in x and then -4 units in y. Now I'm at 6 units in x, so I'm going to travel down to 0 in x. I'm at 4 in y, I'm going to travel down to 0 in y. So I'm going to travel from this point 64 down to the origin. And that is an important distinction to make. I've started here and I've travelled down to the origin. I've travelled -6 in x and then -4 in y. So my vector is travelling in this direction. You'll notice my drawing's a little bit off, and this is -2b. My drawing's a little bit off, but these lines should be parallel to each other. But you'll notice the direction is the opposite direction. That all comes down to the fact that I've got a negative scale factor here, a negative scalar. So we don't change the direction in terms of the angle, the gradient of the line, but by having a negative scale factor, we do reverse the direction of the vector. So if this was vector A, for example, negative A is the same vector A, the same gradient, if you will, and the same length, but it's in the opposite direction. We'll actually come back and talk about that in a second, because it relates to something in a previous earlier video that I mentioned. But anyway, getting back to our subject at hand, so if we have a negative scale factor, we're going to inverse the direction of our vector. But you'll also notice, if I was to look at b here, we know b travels 3 units in x and 2 units in y. So if I started here at the origin and travelled 3 units in x and 2 units in y, you'll notice I travelled to this point on the vector -2b. If I travelled another 3 units in x and 2 units in y, I travel to the end of that vector. So you'll notice that our length is twice the length of b. We still have twice the length of b, but our direction now is in the opposite direction. So this comes back to why I wanted to take the absolute value of our scalar. And that's because you saw when we had a -2 as our scale factor, the length wasn't scaled by -2, it wasn't a negative length, it's still a positive length, it was twice as long. So we ignore the negativity of that -2 and we simply leave it as a +2 times the length of our vector. So when we had a scale factor of -2, the length was just 2 times the length of our vector. Where the minus is really important is the fact that it inverses the direction. It goes in the opposite direction to the original vector because that scale factor is a negative. So once again, if we have a scale factor, that scale factor, the size of that scale factor is going to scale the length. Whether it's positive or negative, it doesn't matter. If we take the absolute value, the size, if you will, of that number, it's going to scale the length of our vector by that size. However, if it's a negative scalar, a negative scale factor, the direction of our vector is going to be reversed. It's going to go in the opposite direction. Now, a second ago, when I drew a and minus a, I actually mentioned that I wanted to come back to this and refer to an earlier video. The earlier video I wanted to refer to is when we talked about 2D vector subtraction. If you recall, just for a second as I sidetrack a little bit, if you recall, when we had vectors and we were subtracting them, for example, if I had a vector a and I was subtracting vector b, we said we take our vector a in terms of our graphical representation. And when we get to the end of the vector a, if we had a vector b, for example, that looked like this, we said instead of placing vector b so that it starts at the end of where we'd got to, we actually place it so that it ends at the end of where we'd got to, but we travel in the opposite direction down it, so we can think of ourselves as walking along vector a, then walking along the opposite direction of vector b, and if that was our start and end point, the resultant vector would travel between them. So this would be a minus b. Now there's a little bit more of a mathematically rigorous way of showing this, if you will, but I didn't want to get into it at the time because we hadn't covered vector scalar multiplication. Now that we have, we can see that if we had our vector b, we can see that if we had that, was this vector up here, vector b, if we multiplied b by -1, we're going to get the vector minus b. In other words, it's the same vector except for its direction has been reversed. Now, when we're writing numbers, we could say if we had a number, I don't know, c plus, or rather c minus d, if we had number c minus d, we know that we could write this as c plus -1 times d, because we know if we have that, we get c plus -1 times d gives us minus d, and if we're adding a negative number, it's the same as subtracting the number, so we have c minus d. So we can see that in terms of numbers, the same is actually true with our vectors. So if we were having a, I'm not going to have enough room to write that there, so before I get too carried away, let's actually write this down here. If I had a minus b, this is the same as saying a plus -1 times b, which becomes a plus minus b, which of course would then become a minus b. But if we look at this step right here, a plus minus b, or even indeed this step, a plus -1 times b, we know that -1 times b, or minus b, is going to give us this vector right here. It's the same vector as b, same length, almost the same direction, except we're traveling in the opposite direction. So it's the same gradient of line, it's just the opposite direction. And notice we're taking a and we're adding this newly inverted vector to it. So rather than thinking of placing b so that it ends at where we'd got to and we travel in the wrong direction down it, a more mathematically rigorous way of thinking about this is we've got to the end of a, and now that we've got to the end of a, we're going to add the minus b vector. So the minus b vector is the same vector as b, but traveling in the opposite direction. So we're going to take that vector, which is minus b, and we're going to add it just the same way that we've done any other vectors, which means wherever we've got to, we place the start of that vector where we've got to and then travel along the length of it. But because it's minus b, instead of traveling up the length of b this way, we're travelling in the opposite direction. So it's the same concept, if you will, as placing b so that the end of b is where we are and we travel down the other way down b. But really, the mathematically rigorous way of showing this is actually that we have the vector minus b, and then we can think of any chain of vectors as always pointing down a chain. We never have to worry about having some of those vectors pointing in the opposite direction because they were subtractions, because really we're just simply adding the scaled version, the negative scale version of those vectors, so that we always travel down the length of the vector chain such that our arrows are pointing down the length of that chain. So really, both ways are perfectly valid in terms of the graphical representation. Whichever way works better for you, they are perfectly valid. But the mathematically rigorous way, if you will, is to think about it as being a vector times by -1, scaled by -1, which gives us this negative vector, so that we think of it just as an addition of vectors, but we're adding a vector that has been scaled. So that's the mathematically rigorous way of looking at it. And I wanted to bring that up here because, of course, we hadn't looked at scaling a vector. We hadn't looked at multiplying a vector by a scalar until this point. So it did really seem like the appropriate occasion to jump back to what we'd already looked at and then show truly the mathematically rigorous way of looking at that. But that's going to pretty much conclude everything I wanted to cover in this video. So if I scroll down, let's just go over the key concepts again. So the key concepts were, if we have a vector which has the components x, y, so it's a 2D Cartesian vector, and we have a scalar, we know that s times the vector is equal to the vector times our scalar, and that's going to be equal to s times x as the first component and s times y as the second component. So again, we take our scalar, and for the first component of the result, we multiply it by the first component of our vector. For the second component of the result, we multiply it by the second component of the vector. So again, vector scalar multiplication is commutative, and the result is equal to multiplying the scalar by each component in the vector to generate the corresponding component in the result. We also saw how this affects the graphical representation, noting that it doesn't change the direction unless, of course, it's negative, in which case the direction is reversed, but that it does change the length of those vectors, and the way it changes the length of those vectors is that the length of our vector multiplied by a scalar is equal to the absolute value of the scalar multiplied by the original length of the vector, which is just a fancy mathematical way of saying if we multiply by a scalar value of 2, it's going to be twice the length. If we multiply by a scalar value of 4, it's going to be 4 times the length. If we multiply by a scalar value of -3, it's going to be 3 times the length. We ignore the fact that it's a minus, but that minus means that we have inverted the direction. We're traveling in the opposite direction than we were originally. And with that, that is going to conclude the theory of this video, but I guess it'd be worth setting just a couple of questions for you guys to work through, though everything here is very simple. I'm not going to worry about the graphical representations of these vectors in terms of these questions, though of course if you want to, feel free to draw the original vector and the scaled vector and to see, do these follow along with what I've shown so far in this video. I assure you that they do, as long as you make sure you take your time and take care when you're drawing everything. But I'm just going to go through and work with the components here on the whiteboard. So the first question I'm going to set, I'm going to give you a vector. That vector is going to be A. And that vector is going to have the components, 10 and 5. And I'm going to give you a scalar, and that scalar is going to be 2. So what I'd like you to do is I'd like you to calculate the result of s times a. Now I know this is a very simple example. In actual fact, they're all going to be simple examples, but it just makes sure that you do fully understand everything that we've covered in this video. So go ahead and pause the video, give this an attempt, and once you have a solution, then unpause the video and I will work through on the whiteboard. Okay, welcome back everyone. So it is a very, very simple question. There's nothing complicated that we've seen really in this video, especially in terms of components. There's nothing complicated. But just to make sure that you did understand everything fully in the video, hopefully you've gone off and answered this question. And what you should have come up with is that s times a is equal to 2 times the vector 10, 5, which we know is going to give us a vector with two components. The first component is going to be equal to our scalar times the first component of the original vector. That's 2 times 10, which is 20. The second component is going to be equal to a scalar times the second component of our original vector. That's 2 times 5, which is 10. So you should have got the vector 20, 10. And if you were representing these graphically, you should have got a vector with the same direction that was twice the length of the original. So that's the first question. Nothing to it really. I'm going to set just one more question because again there's really nothing to these questions. In this case we have a vector b, and this vector is going to have 4 in x and minus 2 in y, and the scalar value I'd like you to multiply this by is going to be a negative 3. So I'd like you to calculate s times b for me, please. Okay, welcome back everyone. So we know s times b is equal to minus 3 times our vector, which is 4 minus 2. And we know that's going to be equal to a vector with two components. The first component is going to be equal to minus 3 times the first component of that vector. That's minus 3 times 4, which is minus 12. The second component is going to be equal to minus 3 times the second component of our vector, which is going to be equal to minus 3 times minus 2, which is minus 3 times minus 2, of course, is going to be positive 6. So that's a positive value of 6 because the two negatives cancel each other out. So our result vector is minus 12 and 6. Fantastic. So really, again, nothing to it. Hopefully you had no issues following through and answering that question. If you did get stuck at any point, if you did have any problems and my working through it didn't clarify where you went wrong, then please do rewatch this video and just make sure that you fully understand how we multiply a vector by a scalar, as well as understanding, I guess it's quite important to understand the graphical representation, the fact that we're actually scaling the length of this vector, which is very useful. It's very useful when you're trying to solve problems to know that if you have a vector and you multiply it by a scalar, it's going to scale up the length of the vector but maintain its direction. But of course, if you have a negative value, it's going to flip the direction, and that again is very useful if you're solving problems, especially problems in computer graphics. It's good to know that we can scale up a vector, we can flip the direction of the vector by using a negative 1 as a scale factor rather, so that is very, very useful. But with that, that is going to wrap up this video, and in the next video we're going to take a look at unit vectors. Thanks a lot everyone.